Okay, so today's class, we will essentially model a double pendulum. Then we will, I'll show you how to access the system dynamics in MuJoCo. We'll check the energy, we'll check the equations of motion, and eventually we will do control, we'll do torque-based control. There are three types of control. We're talking about position derivative. Then there is gravity plus Coriolis forces compensation, followed by PD control, and then feedback linearization. Okay, and the extra thing here is we're going to write data, a data file in a way such that MATLAB can read it, and we'll make plots because we want to check energy and how it varies with time. And the best way to do it is to write a file which MATLAB can read. Okay, so this is what you need to do. I created a new template. It's called template_writeData.zip. As usual, go to tiny.cc /MuJoCo, download the template.zip. Then we'll give that folder a new name, let's say db pendulum, and then we'll rename the pendulum.xml file. This file was created last time when we did a simple pendulum. We'll rename that to double pendulum. Then we'll make a few changes in the file so it's compatible with our new folder name and XML file. And we'll run it in shell and see that the single link pendulum which we created in the previous class will show up. So once we do that, we can then go ahead and modify XML file as well as the main file to do what we are trying to do in this lecture. Okay, so I'll do it and you can follow, or you can do it yourself now that you've done it a couple of times. Okay, so here is my project. I dumped the template_writeData file. I'll call that db pendulum. First step. Next, we open this. We will open the, well, we will rename the pendulum.xml as a double pendulum. The next, so that's the first change. The second change is we need to open main.c. Here it is. Okay, this is the main.c in the folder I copied. Here, what we need to do is we need to rename this folder to whatever we called it, db pendulum. And then since the XML file will be called double pendulum, we'll rename that. Okay, and no other changes are needed. Okay, close this. Now open the make file. Uncomment the appropriate stuff for your operating system. So I'm using Mac, so these 3 lines are uncommented. Change this root name to db pendulum. Close that. And then the final change is pick up the right file for your operating system. So for a Mac, we open run Unix. And then change that template_writeData to db pendulum. Is the name of the folder we just created. Okay, that's it. So once you have done those changes, open a new terminal window or x64 shell. Navigate to your MuJoCo folder. So for me, it's in documents, MuJoCo 200 macOS, my project. And then since I called it double db pendulum, I'll say db pendulum. Okay. So you can check the directory by doing pwd. So right folder. And now we just do /run Unix or run win, depending on your OS. Okay, so this is what we had created last time. This is the pendulum with with the it's in the upright position, and it's not falling down because it's perfectly balanced. So if you perturb it, it'll actually start oscillating. Okay, so now let me open up the important files. So we'll be editing double pendulum and eventually main.c. So, okay, here is that file, exactly how we left it when we talked about the single link pendulum. Okay, so a few things first. Let's just get rid of the actuator and sensor. That is, we will just comment it out. So the easy way of putting a comments in Atom is to use the shortcut. For Mac, it is Apple key and backslash. But other way you can do it is highlight the part, and I believe there is an option somewhere on the top. Edit that. So that will comment it out. Or you can type these things to put a comment. Okay, so we will get the actuator back in, but for now, let's try to model a pendulum without any actuator so it falls freely. Okay. Okay, next we will, let me get that pendulum back to its vertically downward positions. Remember, we rotated it by 180 degrees to make it vertically upright. So with this change, let me just run the file, run the main file again. So run, need so much space, organize my desktop. Okay, so run _ Unix. Didn't seem to have made any changes. Okay, I modified the right file. I'm going to check this. Let me put 30 degrees and see if there was any change. Oh, interesting. That did look like it's the same file. Somehow something makes me feel that it didn't quite rotate by 180 degrees. Now that the space seems to be the same. Let's do one thing. Let me move this down a little bit. Okay, so that's 0. And let me now rotate it by 180. It doesn't look like it's changing anything. Okay, let me just start, keep moving on, create the second link, and then I can debug. The other thing I can think of doing is, it's more handy to use simulate to look at the joint axis, and sometimes that gives a clue. So let me just, instead of trying to do this with main, let me just go to bin and run simulate. Let's drop the double pendulum. We can see the axis rendering. Okay, the joint is right there. Zoom out. Okay, that's 0. Change that. Everything looks like that it should be downwards. So let's reload. Yeah, I see I think I know what's going on. It's just that the joint actually moved up. I see. So this is right. What I'm doing is not incorrect. Okay. So we have this now. We need to create another link which is down, but you can see that if I make the link down here, it's going to collide with the ground. And so what I'm going to do is I'm going to move this up by if I move it by 1 more meter, then I can get a 2 meter long pendulum, but it will maybe just hit the surface. So what I'm going to do is I'm going to move it fairly up. I'm going to move it to 2.5. Okay, so that way it's safely above 0.5 meters from the floor, even when it is full, it's downwards. So we did that. Let's not check that, but let's create another body, which is the second link. Now, something to remember here is this is a serial link chain, which means that the second body is connected to the first body being the green pendulum, and that green pendulum is connected to the world, right? So that's why you see this nested structure. So the world body is connected to body, which is our pendulum link 1, which then has to be connected to second one. So what I need to do is before I close this body, that is the green pendulum, I need to create another structure, another body, which is my second link. Okay, as so, and let's just put 0 for now, 0, 0. And then I need to give it a different, the joint axis a different name, other there'll be a conflict because this is already called pin. So let's call it pin 2. The type is hinge. The axis is okay. It's along the negative y-axis. The position is, this is a joint, the hinge position. So just keep it at 0. And then we modify cylinder size RGBA. Now, if I make it green, then it's going to look very odd because you already have a green pendulum. So let's just change it to, since we have the floor is red, let's change it to blue. So RGB, B is this. So let's just change it to 0.9 and move the second one to 0. Okay, and so if everything looks right, you should see two pendulums, one on top of the other. So let's reload. So that's how it looks. It's the pendulums are one over the other. The axes are slightly displaced. That's why you see that the joint is different at a different location. So what I'm going to do is I'm going to start to move the. I'm going to try to move the pendulum, the second pendulum downwards. Okay. So for that, what I need to do is I need to work with with the body position. So this. So join. Okay, so this is basically the position of the first body. It's 2.5. What I need to do is move this body by. So remember that in each geometry, the center of mass is right in the middle of that cylinder. So, for example, here the center of mass is here. So if I want to move the second body, I need to move it in such a way that its center of mass is, since center of mass is midway, I need it to move a distance of 1 meter from the first one, right? So that way you will have the distance between center of mass of pendulum 1 to the distance of center of mass of pendulum 2 is going to be 1 meter, 0.5, 0.5. So let's do this. Let's put, in this case, 1. Let's see what happens. Okay. So it looks like the pendulum appeared, the second pendulum appeared on top of the first one. It's really hard to distinguish which of these joints corresponds to which of the pendulums. Let's see if I can light world body now. Okay, I need to basically guess which is what. Okay, so then we've done that. Now let's try to move the joint axis. So in order to figure out which is which, we can just try to move one of them, and the one which moves when you change the location is the one which is we're trying to move. So let's move the position of, let's say, pin 2 to position here, X, Y, Z. So we're only dealing with the Z axis here. So that's 0.5. So keep this in mind. I'm going to reload it quickly. Okay, looks like that. So I moved the axis the wrong way. So this is connected to the world. So what I really need to do is I need to move this axis down and this one right here. And this is exactly opposite of what I wanted it to be. So it looks like there's some problem with this and also with that one. So let's just work with joint one first. So I'm going to change this to how about changing it to minus 0.5 and see what happens. Okay, that looks right. And it seems like I moved this to opposite direction. Okay. Okay, now let's see if this actually falls when I rotate it by an angle. So let's just move this by 5 degrees. Looks okay to me. And it's not hitting the floor. It's interesting that it is actually penetrating itself. Okay, so we don't need to do anything with context, but it's fine going within the other one. This is what we wanted. We didn't really want to mess it. Now, if you don't want this to actually collide with the other one, what you can do is you can actually move in this case is the y-axis. You can move the y-axis of the joint slightly. So if you want to do that, you can just do that quickly. Let's go to joint and move this y-axis at this position by 0.1. Let's see what happens. I mess it up. I need to pause. It looks like it moved in the wrong direction. Oh, let's go back to 0 and reload. And now we can make sense of this. So now we want to move it slightly forward or backward. I thought it was the y, but what I think I changed x, my bad. So I need to change y. So let's change the pin to 0.1. Reload. Oh, that just moved the pin. I see. We probably don't want to move the pin. We want to move the body. So let's do this. Revert back and change the body to 0.1. This will work. Yeah, this if some people like it this way, or you can move it the other direction. Okay, this looks good. Let's just change this to 5 degrees and reload. Interesting. It doesn't. Oh, it's like positive. So now maybe it's more realistic where the pendulum is not really colliding with the other one because there's enough gap. Okay, so you get the idea. You can change that. Pause. All looks good. Okay. Let's go back to that folder. So cd.cd my project. It was db pendulum, and then run Unix. Okay, so the pendulum looks just like it looked earlier. The only thing I need to change here is the view. I need to move the view a little bit up, and that option, as I said, you can play with it yourself by looking at the cam dot look at one. And I think in this case, all I need to do is move it slightly up. So if you go to main dot, in the main function within main.c, then you would just need to change the z positions. Let's just change it to 3 and see what happens. So this is line 224 in main.c. That's too high. So let's lower that to maybe 2. I think that's okay. just stick with this. Okay, now one thing which I forgot to do is let me just go back and change this to, please do this change because it's important. If you go to body position, I actually tilted it by 5 degrees. I don't want to do that. I want it to be perfectly aligned with the vertical. So please change this back to 0. Line number 8 in the XML changed to 0, 0, 0. So if everything looks right, and if you go and run Unix, then you should see that the pendulum is upright and it won't move. Okay, so you should have this. This is what you see when you run Unix. It is the right thing. Okay, so now let's get started with the actual things we're interested in doing in this class. First of all, let's check energy. This is a pendulum without any torques applied to it. So the energy as expected should be constant, right? That is, you need to take the potential energy, mgh, the kinetic energy will be half mv squared plus half I omega square, and the sum of that should be constant. Now, you could do that calculation if you know the mass, velocity, angular velocity, and inertia, but MuJoCo does that for you. So we'll just use the function within MuJoCo to get it. And so the way you access this is this function called mg energy pose and mg energy vel. Okay. So again, you can, if you can find this in the documentation. Just going to open that. So this would be in the API reference. MJ energy pose and MJ energy val. You need to pass the model and data. Okay, so let's do that. Energy pose. So go in. So I've done this work for you. That is, I created my controller where you're going to do the controller callback. So that's line 50. So go to line 50 and copy paste MJ energy pose. So this is just telling MuJoCo that I am now interested in you computing the potential energy, and I'm also interested in you computing the kinetic energy. So that will be well. Okay, so when you write this commands, it goes internally and does that computation for you. So you need to call these functions. Once you call this function, the question is how do you access the energy? So I'm going to search if there's an energy variable. Okay, here it is. So just like there is time, there's energy, and there are two. It's an array of two variables. One is potential. The first one is potential. The second one is kinetic. And then the question is, where is this stored? It's, if you go down, you'll see that it is stored within, in data. So it belongs to the data structure. So I need to access it this way. It will be d pointer to energy 0. This would be potential, and the 1 would be kinetic. So I want to print this out. So I'm going to do is printf %f. So I'm going to do is I'm going to print, let's see, I'm going to print the time first. So for that, d pointer to time. Okay, so that's going to print time. Then I'm going to print this value, the potential. Then I want to print the kinetic energy, so that would be 1. And then you know that those are by themselves not constant, so I need to sum them up. So sum this with kinetic, and I need to write the appropriate number of variables here. So there are 1, 2, 3, 4. So I need to do constant f, and then new line. So it will print each of these values at a new line. So let's, with this change, let's try to run this. Okay, so you see that Okay, so nothing is moving, right? So we don't want that. We want a thing to move. So what we'll do is we'll first change the initial position. So let's go down and change the initial position like we've done before. You can do it any time before this while loop. So what I'm going to do is go to main just before the while loop, change the position to DQ pose. And since there are 2 degrees of freedom, so I'll set 0 equals, so this is the first link. I want to tilt it by, let's say 0.1 degree, sorry, 0.1 radians. And then I don't want to do anything to that. So I can either put 0 or you can just leave it like this, it doesn't matter. Okay, so with this, let me run this. Now it should freely move, as you see, but it's kind of interesting that the energy doesn't change. And the reason it doesn't change is because we only told it here in the main file that we need the energy. We also need to make a change in the XML file. Okay, so the change you need to make is you need to tell that MuJoCo that needs to give us the energy. And so that is actually a reference in the XML. So if you go to XML, then search for energy. Okay, so there is flag energy. So let's see what this is. Energy. So you need to tell whether energy is enabled or not. So unless you enable it, it's not going to compute it. So by default, it's set to disable. So within MuJoCo XML, I need to set this flag. So let me go back to the XML. And here, when I put sensor noise, by the way, I can delete that. I don't need sensor noise for this example. I want to put energy equals enable. Okay, so make this change in the XML in the chat. And now let me go back and run this. So what I'm interested here primarily is the column number 4, which gives me the total energy. And so, okay, so this is actually stopped at 5 seconds. So what I did was my new file, I'm actually limiting how much time I want this to run. So you can change that easily. Let's just change it to a really big value. So you can see the cement that's set to 5, and so it's stopping in 5 seconds. Let's make it, let's make it 50. And let's run this. So I want you to observe the energy. So it's looking good there on the animation, but you can see the energy, it's going 57, 56, 53. That's not good news. It means that it's losing energy, which is not what you want for a physics simulation. Okay, so actually have figured out why that's happening. It's because of the integration. So you are more accurate, the more shorter the time steps are. So if you look back into the documentation, and if you, there's a something called time step, option time step, and you can see what this is. So time step is 0.01. That's a really big time step. So what I'm going to do is I'm going to increase the time step and then see how this changes. So go to XML. It's in option, I think. Let me confirm that. Time step equal to point. So it was 0.001. So let me make it 0.001, which is at which is basically at 1 hertz. Sorry, 1000 hertz, right? 1000 hertz, 1 millisecond. So now let's run this. 58, 57. It looks like it's decreasing, but it's decreasing much slower than previously. Now it's just gone bad. Okay, let's just make it zeros. Add another 0. Okay, look at the energy, the 4th column. And that looks pretty good. You can see that it's more or less 58. And then there's 41, 30 on the second 2 decimal places, the first digit after the decimal place. And now it looks like it's decreasing. Oh, now it just fell down. So I don't know if this is to do with contact. that was strange. I didn't expect it to decrease, suddenly stop there. You know what, since we have this issue, let me just do something which is disable contact. I suspect it's something collided with something else. So let's do contact equals disabled. Okay, so you can check this in the XML reference. Now see if it changes. Yeah, it looks like it was the contact flag. There was a collision and that dissipated all the energy, but now it looks good. The energy is still decreasing, but it's sort of stabilized. Okay, so another thing here, which is there's an integrator which is using is actually called the Euler Integrator, which is actually pretty inaccurate. So you can actually change the integrator to be a different one. Let's see what the options are. I think it's somewhere here, integrator. Okay, so there are two integrators. There's the Euler and there's RungeKo API. Now, Euler is the inaccurate one. RungeKo API is the more accurate one. It's just that RungeKo API requires more resources to do computation, so it might get a little slow, and that's why people actually in the gaming industry use Euler. They don't use RungeKo API. So if you want to actually check the energy and if we care about energy, I would suggest using RK4. So what I'm going to do is I'm going to just change the integrator to RK4, and that has to be done in the same place as here. So I change the integrator equals RK4. Okay, and the same time step. And you saw that was changing in the first decimal place. Now let's see what happens. Here you can see that it's pretty much solid now. It's not changing. It's changing in the fourth or fifth decimal place. So that's pretty solid. Let me stop this. Let me send this new XML file via chat. So I dropped it in chat. Okay, now there's another, so you can just swap your XML with the one I sent it. Now, there's something else which I wanted to show you, which is, well, first of all, let's just get this back to 10 from 50. The other thing I wanted to show you is I wrote a function which helps you to, a function which helps you to save data. Let me just send this file by email. Okay, send it by email. So I wrote a function which saves data. And so what I've done most of the work. The only thing you need to do is you need to tell which variable you're trying to save, and you need to tell it and actually go ahead and save it. So if you scroll down and look at this function called init save data, go to the init save data on line 128, and then we will tell it that we want to save, let's see, TE first, KE second, and TE third. So put this down. So that's line 128 on the folder, the function at 128. And then we'll go down just below that called save data. And here we'll actually tell it what exactly is the data. So %f, 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 that's for the three things. And then we will essentially copy paste this, d energy 0, d energy 1, and then the sum. Okay, so there's two changes. So we copy this. So this is the function. Okay, so now we are all set to, well, run this. So it's going to run for 10 seconds and stop. Stop. Now what you can do is you can open MATLAB. Okay, and open the folder. What it does is essentially writes this file called data.csv. That file, data.csv, if you open it, you'll see that it has 4 columns, one for time, one for potential, one for kinetic, and one for total energy. Okay, there is a problem here. It didn't really write 3 columns. It wrote 3 columns for this, but didn't write 3 columns for the second line. So I know what the error is. So let me close this. The error I made in main.c is the following. I need to actually put a comma here. This is just to say that's a delimiter for CSV. So change that. I'm going to send this back. And now we'll run it again. So it runs for 5 seconds and stop. Sorry, 10 seconds. Okay, it stopped. Now go back to data.csv, open it up. This is what it looks like. So now it's nice, it's in different columns. Okay, so we got the data. Now we wanted to plot it in MATLAB. So what I've done is, close this. So I've actually made this file called main.m, which actually does this plotting for you. You just have to run it. You don't have to do more than just running it. So open MATLAB. Open this in MATLAB. Okay, and then run it. Okay, so it produces this plots in a different. So it produces this figure. So the first figure is, so what I did was the time here, each of those things are plotted on the y-axis. So time, for example, is here, there's PE, there is KE, and then there is T. Okay, so time, and the x-axis is just the number of rows. Okay, so time goes linearly, then you have PE, which is all funky, K is funky, but the sum is almost constant. Where this, if you zoom it, you see that this is like 58.7618 to 58.762. It's like it looks like a spike, but really this is, in the grand scheme of things, this is like a small change because the x-axis are accordingly very small. This variation is 1e -4. So it looks good. Now, if you want to make time plots, then there's a simple change you need to do with the MATLAB file, and this is the change. The first index here is always time. So all I need to do is, let me just make a copy of this. So I'll change the first one to, that's the time, and this is whatever variable I'm interested in, and I want to go from 2 to n. So this n is basically the number of columns. So in this case, the first column is time, and I don't want to plot that. And then I need to put x label as just the first index, which is time. So if I do this now, I'll have plots against time. Okay, so now we have t versus time, k versus time, and PE versus time. Okay. There's another thing which I wanted to show you, which is This file is 1.7 MB long. It can be made long and short depending on how much time you want to do this, but you can also set another variable as to how many, what is the frequency at which you want to save data. So there is another variable here called data frequency. So this basically takes and saves one data point every 10 iterations, right? So if you want to have more data, you want to decrease this. If you want less data, you have to increase this. So let's make it 50, which is 5 times as less data as previous, and run this. If you run this now, remember the file size was 1.6 or 7 MB, and I think now it will be 1/5 of what I had earlier. So it'll be 0.3 MB. So go back and check this. So it's just 340 KB. So it's 1/5. Okay, so that's that. Let's move on. Okay, the next part is we're going to check the equations of motion, and this is actually important if you want to do any model-based control. So what are the equations of motion? Well, equations of motion for a system like a pendulum will be something like this: mass times acceleration plus c, which is the Coriolis forces, g, which is gravity, equals the external forces. So we have m here is 2x2 matrix. Q dot is acceleration, which is 2x1. Coriolis is 2x1. Gravitational force is 2x1, and then external force is also 2x1. So you can see that dimensionally they're consistent. Now, this is how MuJoCo has its equations. You can access the mass matrix. You can access the acceleration, which it computes. You can access the sum of c plus g. So it's unfortunate that MuJoCo does not give you g and c individually. It only gives you the sum. So if you're doing gravity compensation, you just can't do gravity compensation by itself because it gives you the sum of the two forces. And then there are two ways you can apply torque. You can use a FRC applied, which is a generic way of applying a torque, or you can use an actuator. You can define an actuator in XML and use control, but they basically do the same thing. So you can use one over the other. It's up to you. Okay, so let's see how to check the equations of motion. And my goal here is to show you how you get m, how you get acceleration, how you get this term. And then, since this pendulum has no forces applied, the sum of these two things on the left side should equal to 0. So we'll check that. Then I'll apply some force, and then I'll show you that the left side equals the right side when you have applied force. Okay, so let's do that. And I'm going to do this slightly faster. I won't really go back to the documentation, the API to do it, but after I finish this, you can go back and check the documentation, how I came to that. So let's check the equations of motion. Okay, I'm going to go slightly fast on this. Okay, so I'm going to check the equations in every time the loop is called, which means that the best place to access this would be in my controller. So I'm going to comment out the printf. I don't want it to print anymore, but it's still saving the data. I'm not commented that. I'm going to check equations here. So here's how so what I need to do is get the mass. So mq acceleration plus q frc equals q frc applied plus CTR. So I'm going to just access these things on the left side first, and then I will compare them against the right side. Okay, so first, double So what I did here is I'm allocating memory here. NV is the size. NV equals to NV is the size of my system. So it's a 2 degree of freedom system. There are 2 links. And so the mass matrix is going to be 2 by 2. Now, the way MuJoCo saves this data is not as a 2 by 2 array, but it saves as 2 times 2, 4 variables. So it's saved as a one-dimensional array with 4 variables. That's why it's written like this. Now, what I can do is there's a command called mj full m, and again, I won't go back to the documentation and check it, but you can go back and check it later on. The way this works is you pass it to it the model, you pass it the variable which you want it to save the mass matrix, and then you pass this particular qm. So this is the dimensions of the mass matrix. This is a inbuilt variable which is saved in the data, and it is used to access the mass matrix. So that basically what this function does is it takes this initialized array and puts in the mass matrix as a one-dimensional array. If you want to access that array as a 2 by 2 matrix, what you can do is double m nv, which is a 2-dimensional array, initialized to 0. I should put 0 here. It's initialized to 0. And then if you want to access it, it's basically m 0 equals, that would be the first one. That would be dense. So there are 4, so I'll copy it 4 times. 0, 1, 2, 3. And I would just save them as 0, 1, 1, 0, 1, 1. That is I'm putting in the row column format. Okay, so if you want to check this, go and say printf, %f, new line, 0, 0. That's the first column. Then 1, 0, 1, 1. And then just to demarcate it from the next entry, just going to put this, just a filler. Okay, so if I run this, it should print the mass matrix. Let's just go and run. Okay, error. Undeclared identifier. Oh, I need to say int. Variable. Okay, so the problem is I have to, since it's allocating memory for an array, I need to initialize this such that it doesn't change. So I think const will do it. So if you're not interested in this, just this. So this is the mass matrix. You can see it's symmetric. The row 1, column 2 is the same as row 2, column 1. And if you go and check the equations of a two-link pendulum, you can verify that these are actually right. Okay, so that's the mass matrix. Okay, now what I'll do is I'm going to save the. Okay, so I'm going to get the acceleration. So let's double q, and I'm going to call it q double dot, indicating the acceleration. So nv equals 0. The easy way to access that is qd dot 0 equals. So this is again in the documentation. The way there's a variable for q acceleration. It goes by the name QACC. And then you can get the first one. So this is getting the acceleration right from MuJoCo, just provides it to you. Next, what I'm going to do is I'm going to club I'm going to find the QFRC bias. So my goal is to write this as m times q dot plus f equals this whole thing. Okay, so let's get this. So I define double f nv equals 0, and then f0. So again, there's a variable which saves the right-hand side, FRC bias. It goes by Q FRC bias 0, and F1 equals the Q FRC bias. Okay, so I have got this part, I've got this part. I just need to take the product first and then add it to F. And that's what I'm going to do next. So let me define my left-hand side as another variable, mv equals 0. And this is going to keep track of the running sum of this things on the left side. So first I will use it to store this product. And then when I get this as add F to it, that will be my left-hand side. So here's what I'll do. There is a utility to multiply a matrix with a vector, right? M is a matrix. This Q dot is a vector. And again, it's in the documentation. I'm just going to use it here. MGU, it's called mul matrix to a vector. I want it to be saved in LHS. The matrix is tens M. So this one, it's I should give it the way MuJoCo wants it, which is a one-dimensional array, and that's why I put it here. And then I need it to multiply this with Q dot, and I need to also tell the dimensions of this M. So it's 2, 2. So this basically gives me M LHS equals M times Q dot. So that's available. Now what I do is I sum it with just 0 plus F0. So what I've done here is effectively I've taken LHS equals M QD dot, which is already computed. Now I'm just going to add F to it. So I need to do it for the first line, and I need to do it for the second line. Okay, so having got that, now I can do printf, %f, new line, LHS 0, LHS 0, LHS 4. I'm just going to do this so it's easy to see each line. Okay, so now the expectation is if everything is right, then LHS 0 should be 0 and LHS 1 should be 0, because that's the equation of motion, right? There's no force acting on it. So let's see what happens. Okay, QACC looks like I did not define it quite right. Let's try it again. Maybe another error. Oh, it looks fine. Okay, we are interested in this. So you can see there is this thing which is it's 0 sometime, it's not 0 sometimes, 0 sometime, not 0 sometime. And this is actually something to do with the accuracy of the integrator. So you can check this easily by going here and then making this crazy accurate. So I introduce one more 0 here. Now let's run this. So you can see that the animation is going slowly because the time step is really small, but it's more accurate than previously, right? You can see it's almost 0. Okay, so I don't want the animation to go so slow. So I'm going to get back to what I had earlier. Okay, I'm happy with this. Okay, now let's just add QFRC applied. Let's see if we can add a right-hand side. Something on the right-hand side as a force. Okay, so the QFRC force is an input which you give, the QFRC applied, and you can specify it to be whatever you want. So give that would be the torque. Okay, now one thing we can do is, since it starts with a slight tilt of 0.1 degrees, if you want to make it stop there and not move at all, what we need to do is, if we can apply a force exactly equal to F, so it cancels the Coriolis and the gravity force, then it will not move, it will just stand stably, right? So the simplest thing we can try doing here is just put that equal to F0. Okay. So let me comment this out. So if this really works, then you should see that the pendulum will not move at all. No, it's not moving. That's because I compensated for gravity and Coriolis force. If you want to be more convincing, maybe you need to change this Q pose, the initial position, to, let's say, 0.5. So just change it to 0.5. So it stays there. It doesn't move because we've applied force on both joints just equal to the external force. Okay, so with that, let us now, if you want, check the equations with that FRC applied. Where am I? Here. Okay, so if we change that to, let's say, 0.1, so now it's not fully compensating, but somewhat compensating, then you'll see that it moves. So let me run this. It's moving, but it's still, there is some compensation. Now let's check the equations of motion now that we have this. So what I'm going to do is I'm going to print, let me create a new variable called RHS NB equal to 0. And then this RHS will save this quantity, which is whatever force we apply. One. Okay, and now if everything is right, then if you print, say LHS 0, RHS 0, then LHS 1, RHS 1. So if everything looks right, then you should see that the first line you'll have 0 equal, oh, sorry, some non-zero quantity equals non-zero quantity. So these two lines, the first row should be this, have the same value, the second row should have the same value. So let's run this. Let's kill this. Stop. So you can see that it's the same. It's almost the same. It's not quite same. It's off by the second decimal or something like that. And that's because of the integrator, right? If you change the integrator, make it more fine, then you'll see that they're equal. Okay, so that basically checks the equations of motion. Okay. Now, the last thing to do, and I think I'll go like 5 minutes, 5 or 10 minutes overboard. Let's do the last thing, which is use this information to do something useful. So, okay, now that we have figured out how the equations of motion look like, let's apply a few controllers. We can apply a proportional derivative control. So let's say there's a Q reference. Now this Q reference is going to have two things, right? There'll be a reference for the first link, reference for the second link. Then we can do KP, KD, and then get that tau, and then it'll move to that position, whatever is specified QRef. You could do gravity compensation and Coriolis force compensation, which means that you put F and then minus KP, KD for PD control. Or you could do feedback linearization. This is like a more advanced method where what you're doing here is you're taking the mass matrix, you're multiplying it with the PD control, and then you're compensating. So we'll try all these three. And in this particular example, I think they give you very similar responses. Okay, so let's do it one by one. So now we do control. So first let's define KP1 equals 100, KP2, that's the second one, second link, double KV1 equals 100, KV2, KV2 is, I usually like to put 1/10 of the value, but there's a better way to tune that. Okay, so what we want is double QRef 1. So let's say that, so we start from minus, I believe, minus 0.5, 0.5 bit. So we start at 0.5. So let's go from 0.5 to minus 0.5 for the first link. So a set point is minus 0.5. And then QRef2 equals, let's say, so pi divided by 2, 90 degrees is 1.57. Let's do 1.6. So now QFRC applied. So it's not a problem here. It will just overwrite it. So we can uncomment this if you want, but we'll just overwrite. So we have no problem with writing it here. Minus KP1 times Q minus, so Q is Q was 0. That's the angle for the first link, minus QRef1 minus KD or KV1 into times PQ well 0. copy this whole thing. Paste. This be 2, 1, 2, 2, 1. Okay, so let's see what happens. Error. This should be comma. Then these same for this. That's right. It will work now. Okay, I forgot a closing bracket. This is not needed. Okay. There it is. Maybe we can do it minus. It's more interesting, I think. Yeah. So you can see there is a whole bit of wobbling, and you can actually tune it better using what they call an LQR control. Okay, so this is PD control. It's very easy to modify this to do other things. If you want to do Coriolis plus gravity plus PD, all you got to do is comment this is you need to put F0, F1. In fact, you can actually also, what I like to do is I like to write this to a file. So let's write this to a file and see how it looks. So QPOS, so if you go here back to save data. F2def Q1, Q2, and then here printf %f, that would be was 0, T Q was 1. So run this. Forgot something here. So just wait for it to quit. Okay, I don't need to wait for 10 seconds. I can make that 5 seconds. But now if you can go back to the MATLAB function, you don't need to do any changes. You just run this. There is some problem with the CSV file. It looks okay to me. $37. This is something I wrote incorrectly. It's okay. Those commas all look cool. Is this the problem? Let's try this. Okay, there is some problem. I need to debug this, but you get the idea. You need to put it here and it works. Okay, the last thing before we stop is the feedback linearization control. Linearization, which is essentially this. It's mass times minus Kp times Q minus Qref minus Kv Q minus Qref plus F. Okay, so what I need to do is I need to take this first, sum it up, and then I need to do a multiplication of n times that. So I can invoke this kind of trick here with this function in MuJoCo. To use this, where it's called double tau. I will keep track of all my control in tau. Then what I'll do is tau 0 would be this whole thing. Tau 1 would be this line. This. Next, I need to multiply mass with this stuff. So this will be tau. 10 same is fine. What I need to multiply it with is tau. 2 by 2 is right. And then once I do that, I just need to add tau to f. So tau 0 plus equals 1 plus equals f. Then I need to assign this. I need to comment this so that we're sure that it's not being used. This is the only function which controls. Okay, it did something crazy, but it looks like it works. Okay, so that's it. So this is feedback linearization. So we have essentially finished this. So we've achieved, well, as I said, we've created a double pendulum. We have check energy and equations of motion. And why we need equations of motion is because we can then use the equations of motion to do these advanced control methods. Feedback linearization being one of the ways in which you can do very good control. So if you tune those gains actually are to be set so that they're critically damped, and you can actually have no oscillations. And I could have shown you if the MATLAB stuff was working. Okay, I'll stop here.